that she's going to talk about the stochastic perturbations of piecewise continuous map. Please.
Thank you, Jacob. Well, first of all, I am very happy and lucky and thankful for being here, celebrating the anniversary of Welington. And no, eu prefiro usar na mão. Happy birthday, Welington, first of all. I'm going to talk about stochastic perturbation of piecewise continuous maps in a general context of compact metric spaces with no differentiability hypothesis. I suppose that compact metric spaces include one-dimensional manifolds, which is the topic of this meeting. So this is a joint work with Sandro Valienti, Arnaldo Nogueira, and Pierre Guiraud. Okay. Well, the context, as I talked before, is a compact metric space, and A is Borel sigma algebra. It's a measurable space, Borel measurable space, and we denote with M the set of all probability measures endowed with a weak star topology. Let's define a piecewise continuous map with which we are going to work with. We have the compact metric space X, which is partitioned, topologically partitioned, into open pair with disjoint pieces, such that the closures of the pieces, of the open pieces, cover the whole space, compact metric space X. And we have a continuous function from the closure of each continuity piece to X, and the map F, just when restricted to the open piece, is Fi restricted to the open piece. Well, so it is not well defined or multiply defined in the set which is big delta, which is the union of the boundaries, of the common boundaries of the continuity pieces. This is the set of discontinuity points of F. We are going to work not with the iterations of this map F, but we will add a noise to consider a stochastic system by perturbation of F with a noise of level epsilon. What does it mean? Well, we have a point, an initial point, x0, which belongs to some continuity piece of F. We apply F, so Fi0, we obtain an image, and we perturb this image with a noise which is randomly distributed according to a probability which is called transition probability P, which is supported in the ball of radius epsilon centered at this point. So we obtain, after the perturbation, a second point x1, which belongs to some continuity piece x is 1. We apply f again, obtain an image perturbed with a randomly distributed noise, and obtain a second point x2, and so on. And we are going to study the ergodic theory of this stochastic system. We are going to make some mild hypotheses on the noise. We generalize some hypotheses that are usually used in compact manifolds. That first of all, the level epsilon of the noise means that the support of the transition probability is defined or is given as a family for each continuity piece and for each point belonging to the continuity piece, to the closure of the continuity piece, is a probability such that for all measurable set, this is the probability of finding the point x at time n minus 1 in the set A, condition to the previous point is exactly x. So this probability measure depends on the point x and on the continuity piece which it belongs. And we are going to assume that the support, the compact support of this transition probability coincides with the ball of radius epsilon of the image by f of the point x. So it's a noise applied after the map. And the compact support is not a measurable compact. It's not in the measurable sense of support. It's the compact support is the set of points such that the measure of each of any neighborhood of that point is positive. So it is the minimal compact set that has mu measure equal to 1, probability 1. It includes much more points than the measurable support in the measurable sense. It's a topological compact set. The minimum compact set that has measure 1. This coincides with the ball of radius epsilon, the closure of the ball of radius epsilon, centered at the image of the point. The hypothesis we do about the noise is that the transition probability depends continuity on the point with a weak star topology. And the second condition, which is included to avoid multi-definitions of the map, is this one. The set big delta of these continuity points that are here has a transition probability 0. So with probability 0, we are going to drop on a discontinuity point of f. And the third condition, the third assumption here is a mutually absolute continuity, mutually equivalence of the transition probabilities. Sorry, I am used, yes, I know. I am used to use a microphone when I give my classes like here, so I cannot avoid. Yes, I do like this. No, estou bem, obrigada. So, desculpe, sou de utileria, do teatro, assim. The transition probabilities are mutually equivalent. Each one is mutually absolute continuity with respect to the other one in the intersection of their compact supports. That's the hypothesis here. For any measurable set in the intersection of the compact support, the transition probability is 0 if and only if any other transition probability with that compact support is 0. Okay, let's define the transfer operator in the set of bounded measurable functions, in particular for continuous functions, for piecewise continuous functions also. There are continuous in each piece xi of f. We define the transferred function L phi as expected value of the function in the next point of the stochastic orbit. And the dual transfer operator is defined in the space of probability measures. I have to make a correction here. It's not well defined in all the space of probability measures, but you have to consider, to avoid the discontinuities, probability measures such that the probability of the discontinuity, the set of discontinuity points is 0. If not, it may be not well defined a unique measure L star of mu. Well, it is easy to prove, it's a standard, with the hypothesis that the transition probability is 0 on the discontinuity points, that L star mu of delta is also 0. Measure mu is, these are the standard definitions. The only particularities is that the map is not continuous, but piecewise continuous. A stationary measure is a fixed point of the dual transfer operator L star. A periodic measure is a fixed point of L star p, where p is the minimum natural number greater or equal to 1 for which the measure mu is fixed. A measure mu that is fixed for L star p is ergodic if any LP invariant set, measurable invariant set, has measure equal 0 or 1. And LP invariant set means that the characteristic function of the set is fixed by LP. Okay. So now let's state the theorems. First theorem, existence and finitude of ergodic stationary measures. The set of ergodic stationary measures for the stochastic system under the hypothesis I said before is non-empty and finite. The second theorem, each ergodic stationary measure can be decomposed as the average of equally weighted average of measures of an orbit for L star of a measure n, such that n is periodic with period p and ergodic for L star p. Besides, this p can be chosen maximal with that property, the measure n and the natural number p to be maximal. And in such a case, the measure n is not only ergodic for L star p, but also ergodic for any power of L star p. Weakly mixing, can be defined as classically. It is equivalent to be ergodic weakly mixing for L star P is equivalent, can be proved to be equivalent to be ergodic to L for L star P. But here is a little, it's not so weakly mixing because it's also ergodic for all the multiples of L star P. We couldn't prove that the measure nu is necessarily mixing, which was our previous aim. We could only prove that it is missing in the case that the piecewise continuous map, the space is a compact manifold, Riemannian compact manifold, and the piecewise continuous map is expanding. It's differentiable and expanding, C1 expanding on each continuity piece. In that case, we could prove that the measure nu is mixing, which is uniquely defined if the maximal number P and the orbit of the measure nu, not the measure nu, because L aster nu can play the role of nu also. Well, let's, I don't know what time do I have to finish. No. Now 10 minutes, okay. Let's try to make a sketch of the proofs of the theorem. The first theorem, theorem 1, is more or less classical. One only has to, the proof, one only has to avoid the discontinuity points, which are, that's why we put the hypothesis of that the transition probability is 0 on the set of discontinuity points. So the classic proof of existence of stationary measures. First, let us prove that stationary measures exist. Fixed points for the dual transfer operator L star. And the classical Krylov-Bogolyubov method, which is used to prove the existence of invariant measures for deterministic dynamical systems that are continuous, is more or less adapted to this case for the stochastic system of piecewise continuous map. This method is like this. You first consider a seed probability measure, any probability measure that in our case will be such that the set of discontinuity points is 0, and define the average so that in this case you have to apply the dual transfer operators to mu1. And then, as the space of probability measures is sequentially compact, well, it is metrizable and compact, so there exists a subsequence which is convergent, and the method consists, so there exists this measure consists in proving that this measure is invariant, or in this case stationary. Well, to prove this, well, once it is easy to show, it's classical, to show that the total variation of this real signed measure goes to 0 with n. So if this sequence converges to the same mu. So if this converges, well, it's a subsequence, this also converges to the same mu. And the other argument is saying that the operator with which we are working is continuous, which is not our case, and say that to deduce that this converges to L mu. So mu coincides with L star mu. This converts to mu and converts to L star mu. So mu is a fixed point for the operator, which is a problem that in our case we do not have continuity of this dual transfer operator. But this is easily avoidable because we work, instead of working with the measures in the whole compact space, we restrict each probability measure to each continuity piece and work with each continuity piece. Of course, when you apply the operator L star sub I, say that is L star applied to this. This is the probability measure after a rescaling of the measure mu restricted to the subsets, the measurable subsets of this continuity piece. When you apply this operator, you don't obtain a measure that is supported on a continuity piece. But you have then, after applying this operator, you have to decompose the obtained measure into a sum of measures restricted to the continuity piece. It is easy to show by the definition of L aster, I have already told, that this is 0. So when you restrict to the compact pieces, it's the same to restrict to the open pieces. So there is no, you are not adding twice or 3 times the same measure, the measure of the boundary, because it's 0. Okay, so after this, we have to decompose the obtained measure into the restrictions to each continuity piece and apply again to each term the corresponding operator and so on. And in that way, you find a convergence of sequences of each term of the measures obtained restricted to each continuity pieces. This operator is continuous from the space, let's write like this. This is the space of probability measures which are supported on this compact continuity piece. This is continuous. It's a difference of this. So we apply the classical method to each of these operators and finally obtain a measure that is fixed by L star. The second part of the proof of theorem 1 is the proof of existence of ergodic stationary measures. This is rather classical, also with some adaptations. Just to use Klein-Milman theorem, it's easy to see that the set of all stationary measures is weak, star, compact, and convex. So by Klein-Milman theorem, it has extremal points, and which is a little more difficult to prove is that ergodic stationary measures are the same as extremal stationary measures. Because Birkhoff's theorem can be substituted by other theorems about the almost everywhere conversions of iterations of certain linear operators. There are theorems on functional analysis that play the role of Birkhoff's ergodic theorem in the deterministic case for the stochastic case, to prove that extremal measures are the same as ergodic measures. Well, theorem 1 it can also be stated for any power L star P instead of L star. So there exist measures that are fixed by L star P, and the extremal points of those measures are ergodic for L star P. The second theorem. How is the proof of the second theorem? Well, it's really very... Before the proof of the second theorem, I would like to talk about what we were trying to find with the second theorem. Why do we study stochastic perturbations of piecewise continuous maps? Because we have some examples that come from physicists for which systems are not continuous, they are piecewise continuous, particular neural networks, deterministic neural networks, and are piecewise continuous, and when there is noise, it becomes a stochastic system like those we are working here. And some numerical computer experiments made by physicists have proved that in many cases, at least many cases that come from biology, the system has a periodic. You see the figures of those physicists, computer obtained figures, and the distribution of the orbits, which have some noise, very little noise, but have some noise, always look periodic. Maybe with a very large period, but always look periodic. And on the other hand, there are many examples of piecewise continuous maps, in particular piecewise contracting, which are uniformly contracting for each continuity piece, for which the topological entropy of the attractor is defined like this, can be defined like this. This function is multi-defined in the discontinuity points, for which the topological or entropy, I'm talking on the deterministic system, zero noise system, epsilon equals 0. The topological entropy of the orbits in the attractor is positive. And so it's very different from the behavior on the figures of the physicists that every time they see periodic behavior. So we try to explain that periodic behavior, and so we found this theorem. Every ergodic component is indeed the equally weighted average of a periodic orbit, of a maximal period. And this new, well, according to the figures of the physicists, this new should be mixing, but we couldn't prove it's mixing. We just could prove that it's ergodic for all the multiples of L star P. P is the period. How is the proof? Well, it's very easy. Just consider two cases. Take an ergodic stationary measure. 2 minutes? Well, take an ergodic, I have not talked about the finitude in the theorem 1. Well, sorry. I have not proved the finitude of the ergodic stationary measures. Take an ergodic stationary measure. Either it is ergodic for all the multiples of L star, or it is not. If it is ergodic for all the multiples of L star, that equality is immediate, is trivial, with ni equal mu and p equal 1. If not, well, just make some computations and prove if mu is not ergodic for some minimal p, you make the ergodic decomposition of mu, and then prove that that ergodic decomposition is indeed an orbit for L star, so you prove that equality. You prove this equality. And then you take nu and L star p and make the process again and again and again. And so it's enough to prove that you finish in a finite number of steps for that decomposition to obtain a maximal period. And it is indeed, so you have to prove that the period p, that there cannot exist more than k epsilon ergodic measures for L star p for any p. So if there cannot exist more than k epsilon different ergodic measures, the period p cannot be larger than k epsilon. To prove that there cannot exist more than k epsilon is just to prove that the compact support of any ergodic measure for L star p has a complete, a compact ball inside and two different mutually singular measures that are ergodic have pairwise disjoint interiors of the compact supports. So the number k epsilon is smaller or equal than the maximal cardinality of epsilon separated sets. Well, just 2 seconds. Okay. Thank you.